Welcome to the second tutorial of the course. We have discussed about the first law of thermodynamics and basic introduction to thermodynamics in the first tutorial. This tutorial will be majorly focusing upon the second law of thermodynamics. We have discussed about the heat engines, heat pumps. We discussed about the coefficient of performance. Some problem statements on this would be very interesting. So this lecture would be focusing upon heat engine, heat pump, entropy and exergy. Just to revise the heat engine concept regarding the Carnot cycle, a reversible cycle is an ideal hypothetical cycle in which all the processes constituting the cycle are reversible. For a stationary system, as in a piston and cylinder machine, the cycle consists of 4 successive processes, that is isothermal heat addition, adiabatic expansion, isothermal heat rejection, adiabatic compression. These processes are given here. You have gone through this in the lecture series in week 2. Carnot cycle is a reversible cycle that is composed of 4 reversible processes, 2 isothermal and 2 adiabatic. Talking further about heat engine, we saw that in the PV and TS diagrams, that is pressure volume and temperature entropy diagrams, there were the addition of heat and rejection of heat, and because of this lot of things are going on between 1 to 2, 2 to 3, 3 to 4 and 4 to 1. This is already discussed, that is the net cycle heat is equal to net cycle work. That is Q addition minus Q rejection is equal to the WE minus WC. So here efficiency is equal to net work done per unit the net heat addition, or net work done could be put here as heat added minus heat rejected. So efficiency is equal to 1 minus the ratio of the heat rejected by heat added. So from TS diagram we could also see efficiency is equal to 1 minus T2 by T1 into delta S, that is a change in entropy. That is, it finally turns to be 1 minus T2 by T1. Let me see a problem on this to find the efficiency. A reversible cyclic heat engine operates between a source temperature of 800 degrees centigrades and a sink temperature of 30 degrees centigrades. What is the least rate of heat rejection per kilowatt net output of the engine? That is, they are asking the least rate. I need to find the efficiency and I will try to find the value of Q2 because Q1 is there given almost. That is, I will find the maximum efficiency first, then I will try to find the least rate of heat rejection per kilowatt of the net output of the engine. So I'll just quickly draw this engine here. So it is a reversible engine where we have the hot, that is source. We would say this is source. It is the hot body where the temperature is equal to 800 degrees centigrades, and we have the cold body, that is sink, where the temperature is 30 degrees centigrades, in which we have a heat engine in between, that is Q1 enters here to the heat engine and Q2 goes out of the heat engine. So work done is equal to Q1 minus Q2. So it is reversible engine, that is rate of heat rejection is minimum. This is reversible cyclic heat engine. Now we have been given here T1 has 800 degrees centigrades, T2 has 30 degrees centigrades. We need to convert everything to Kelvin. To convert this to Kelvin, 800 plus 273, this is equal to 1073 Kelvin. This is equal to 30 plus 273. This is equal to 303 degree Kelvin. Now to find the efficiency, that is maximum efficiency for the reversible engine, that is equal to 1 minus T2 by T1. This is equal to 1 minus 303 by 1073. This is equal to 0.718. Now we know that maximum efficiency, that is eta maximum, this is equal to net work done by Q1. Now here net work done, this is equal to 1 kilowatt. This means Q1 is equal to 1 by the maximum efficiency that we calculated, 0.718. This is equal to 1.392 kilowatts. Now Q2 is equal to Q1 minus W net. This is equal to 1.392 minus 1. This is equal to 0.392 kilowatts. This is Q2. This is our answer. That is the rate of heat rejection they have asked. Rate of heat rejection, that is Q2. This was asked. We have gotten the value of Q2 as 0.392 kilowatts. Now let us recall the concept of heat pump. Heat pump is a device that transfers heat from the cooler body to the hotter body. For example, your refrigerator. For example, from outside the heat is transferred inside in winters. So heat pump is a device that operates on the principle of transferring heat from low temperature region to a high temperature region. In winter, heat pump can move heat from cool outdoors to warm a house. So that is, a work is to be done over it. Some mechanical energy is to be put in it so that a heat transfer from the lower temperature region to a high temperature region. The relation of work done to heat transferred is given below. Work is equal to Q by COP. Work performed by heat pump's compressor is W. Q is heat transferred and COP is coefficient of performance, which is instantaneous at a specific instant. For example, at temperatures prevailing in the reservoir at a specific instant, this is COP, the coefficient of performance. To understand heat pump further, we can connect it to the Carnot heat pump. The Carnot cycle is a theoretical thermodynamic cycle that sets the maximum possible efficiency for any system, that could be heat engine or heat pump, operating between two given temperature reservoirs. It is given by the ratio of the desired heat transfer, that is heat output to the work input. You see, some work is done from outside. From the cold reservoir, heat is being transferred to the hot reservoir. This is heat pump in between, where work turns as an input from the cooler body to the hotter body. The temperature is there. So this is temperature cool, temperature hot. Here coefficient of performance is QH by W. That is general definition. Coefficient of performance is QH by W is QH minus QC. That is also proportional to the ratio of the temperature differences. That is TH by TH minus TC. Ideal coefficient of performance, that is here. Now in this, entropy generation is also there. It refers to the irreversible increase in entropy during any real thermodynamic process. It is a direct measure of the loss of useful energy and an indication of inefficiency within a system. It is given by delta S, that is change in entropy, which is the ratio of Q and T. Q is the heat transferred, T is the temperature. Now let us see a problem statement here. A heat pump extracts heat from environment at 273 Kelvin. and delivers 10,000 kilojoules per hour to a building maintained at 293 Kelvin if the compressor consumes 2500 kilojoules per hour. Determine actual COP of the heat pump, maximum possible coefficient of performance, that is the Carnot COP, amount of heat extracted from the environment, then entropy change of the universe. So, in this we have been given the rate of heat transfer QH is given as 10,000 kilojoules per hour, and we have the temperatures, that is the hotter temperature is 293 Kelvin and the cooler temperature TC is equal to 273 Kelvin. Now, the compressor also consumes 2500 kilojoules per hour. So, this is what, when we talk about compressor, that is the mechanical energy is being induced into, this is we have the value of work W. W is equal to 2500 kilojoules per hour. Let me quickly draw a heat pump system here. There is a building here whose temperature is to be increased to 293 Kelvin, and we have a heat pump here. Heat pump that delivers heat to the building and heat entering the building QH, and there is QC here. There is work, external work or compressor that is entering the system, that is W. This is from compressor. I will just label it. This is compressor work. This is equal to 2500 kilojoules per hour. And in the building, we are making the heat enter, heat energy, that is 10,000 kilojoules per hour. The temperature of the colder part is, that is outer atmosphere, is 273 Kelvin. We have atmosphere here, and this is our building where the temperature, that is hotter temperature, is 293 Kelvin. That's all what is given. Now, let me try to find the solution. 4 things are asked. Actual coefficient of performance, part 1. For part 1, that is for the actual coefficient of performance, we will call it as actual COP. This is equal to COP of the heat pump, that is equal to the energy, that is heat energy, that is delivered to the building by work, that is equal to 10,000 by 2500. This is equal to 4. Then it has asked the Carnot COP, that is the maximum possible COP. Maximum possible COP, that is Carnot COP. This, to recall, is given by this relation TH by TH minus TC, that is coefficient of performance for heat pump, that is maximum is equal to TH by TH minus TC. This is equal to 293 by 293 minus 273. This is equal to 14.65. Then it is asked amount of heat extracted from the environment. Heat extracted from the environment, that I need to calculate, that is QC is to be found. Amount of heat extracted from the environment, that is heat extracted, I call it atmosphere or I'll call it environment. Heat extracted from the environment, that is QC. This is equal to QH minus W, that is equal to 10,000 minus 2,500, which is equal to 7,500 kilojoules per hour. Last part they have asked is entropy change in the universe. That is, I need to find the entropy change in the universe. I will find entropy for the low temperature portion and entropy for the high temperature portion, and then I will find delta S. This entropy is given by this relation Q by T. For both the colder and the hotter body, I will try to find this delta S C, that is for the colder body. This is equal to Q by T, that is Q colder by temperature colder, that is 7,500 by colder temperature is 273. I will put minus here because here the work is entering into the system. This is equal to minus 27.47 kilojoules per Kelvin hour. And change in entropy for the hotter part, I will put it as QH by T hotter, that is equal to 10,000 by 293. This is equal to 34.13 kilojoules per Kelvin hour. So change in entropy for the universe, this is equal to 34.13 minus 27.47. This is equal to 6.66 kilojoules per Kelvin hour. So all the four questions are now addressed, 2, 3 and 4. But this was very interesting problem regarding heat pump. So this was very interesting problem where we saw the heating and cooling systems for the building and how the temperature of the building is risen here. The heat is taken from the cooler environment and it pumps to the hotter environment. Heat pump discussion would stay incomplete if we do not discuss the refrigerator. Let me see another problem regarding the refrigerator. A refrigerator extracts heat from a cold room at 250 Kelvin and rejects it to a room at 300 Kelvin. During each cycle, the refrigerator removes 200 kilojoules of heat from the cold room and rejects 280 kilojoules to the hot room. So just to draw heat pump once again here, we have heat pump, we have sink and source. So here from the heat pump, it flows towards the hotter. We have QH here, we have QC here, and we have the colder body and we have the hotter body. So these values which are given here are this TH is equal to 300 Kelvin, TC is equal to 250 Kelvin, and this is a refrigerator. And we have work in, which is to be calculated. Value of QH is given, that is it rejects 280 kilojoules into the hot room, which is 280 kilojoules. Value of QC is given, that is 200 kilojoules. Now, the first problem, calculate the actual work input. Actual work input, that is I will have to find work input. Work input here is equal to QH minus QC, that is equal to 280 minus 200, that is equal to 80 kilojoules. It's very direct calculation. Next part is determine the coefficient of performance of the refrigerator. Coefficient of performance of the refrigerator, we'll put it as COP of the refrigerator, that is COP is equal to QC by W, that is 200 by 80, that is equal to 2.5. Then comes third part, reversible COP, that is reversible PO to be calculated, COP reversible. So this COP reversible is equal to the Carnot COP, that is temperature of the colder body by the difference between the temperature of the hotter body minus the temperature of the colder body. This is equal to 250 by 300 minus 250, and this is equal to 250 by 50, that is 5. Next part is important again, entropy generation per cycle. So entropy generation, again I will try to calculate in the similar fashion I did it for the previous numerical statement. I will find the entropy for the cold body, it is equal to minus Q cold by T cold, that is equal to 200 by 250, which is equal to minus 0.8 kilojoules per Kelvin. And entropy for the hot body is QH by TH, that is equal to 280 by 300, which is equal to 0.933 kilojoules per Kelvin. So entropy for the universe, that is 0.933 minus 0.8 is equal to 0.133 kilojoules per Kelvin. So all the 4 questions are now addressed here. Now have discussed heat engine and heat pump, I will now try to talk about entropy and exergy in a little more detail. Let us see or recall the concept of entropy. Entropy is a central concept in second law of thermodynamics and serves as a quantitative measure of disorder, randomness, energy unavailability in a system. In simple terms, entropy indicates the degree of spreading or dispersal of energy when energy is transformed, such as heat flowing from hot body to cold one. Not all of it remains available to the useful work. There is a heat rejection as well, that is the loss is reflected by an increase in entropy. In a reversible process, the total entropy change of the system and surroundings is 0, while in irreversible process, which dominate the real world, the total entropy always increases. This was just a recall. Just to recall, how do we calculate the entropy? We take the definite integral of Cp by T dt from 0 to T. That is, Cp is the heat capacity at constant pressure. St here that is being calculated is the absolute entropy. The third law of thermodynamics states that entropy of a perfect crystal at a absolute zero temperature at 0 Kelvin is 0. So therefore, the absolute entropy is integrated from 0 to T, where T is the temperature at which it is being determined. Let me try to see this problem. A substance has an entropy S is equal to 0 at absolute 0. Its heat capacity Cp varies with temperature as Cp is equal to A T power 3, where A is equal to 0.01 joules per mole Kelvin per 4. Calculate the entropy of 1 mole of the substance at 300 Kelvin. Here we have been given S as 0 at absolute 0 and St, as we know, is integral of Cp by T dt from 0 to T, that is third law. Third law of thermodynamics. So that means we need to find the entropy at 300 Kelvin, that is S at 300 is equal to the integral from 0 to 300 of the Cp function here is given as A T power 3 by T dt. Let us take this integral. This is equal to A is a constant that comes outside, 0 to 300 T square dt. This gives me the integral solved here as T power 3 by 3 from 0 to 300. Let me take this difference. Because the initial value is 0 here, so anything minus 0 would come. So this gives me the value as A into T cube by 3 at 300 Kelvin. So putting the values of A and T, A is 0.01, the value of T is 300 power 3 by 3. So this gives me the entropy value S at 300 Kelvin is equal to 90 kilojoules per mole Kelvin. This was a simple problem on entropy. So just to recall the concept of exergy as well, exergy represents the maximum useful work that can be extracted from a system as it comes into the equilibrium with its surroundings. Energy is always conserved as the first law of thermodynamics, but exergy is not conserved as it is destroyed, and you have seen this in the lecture series as well. Exergy, energy and entropy, they all come together. Entropy always increases. Energy can neither be produced nor destroyed, it is always conserved. But exergy is something that is always destroyed. Not going into the concepts into detail, I'll just try to see how do we calculate exergy. The total energy minus dead state energy is the exergy. Dead state means we are talking about standard temperature pressure. That is temperature as 25 degrees centigrade and pressure as 1 bar. That is dead state. In case of steady flow, that is open systems like turbines, compressors, nozzles, the flow exergy or specific exergy per unit mass is given by Ex is equal to H minus H naught minus T naught times S minus S naught. H is specific enthalpy, H naught is enthalpy at dead state, S is specific entropy and S naught is entropy at dead state, T naught is temperature of the surrounding, that is environment when we are talking about a dead state. Let me try to see for the ideal gas, how do we calculate the H minus H naught? H minus H naught for the ideal gas is Cp times the difference between the temperatures T and T0. Cp is specific heat at constant temperature, T is system temperature, T naught is the reference temperature, that is in general the environment temperature, and change in entropy, that is S minus S naught, is calculated as Cp into log of, that is the natural log of T by T naught minus R into the log of P by P naught, where P and P naught are the system pressure and the reference environment pressure. Let us see a problem on exergy. Air, that is an ideal gas, enters a turbine at 800 Kelvin and 900 kilopascals. It exits at 500 Kelvin and 100 kilopascal. The mass flow rate is 2 kg per second. Environment, that is dead state, is at 300 Kelvin and 100 kilopascal. Specific heat at constant pressure, that is Cp, is 1.005 kilojoules per kg Kelvin, and value of R is also given here as 0.287 kg, that is kilojoules per kilogram Kelvin. Determine the specific flow exergy at the inlet and outlet. Exergy destruction rate, that is irreversibility. So, we have been given here the temperature T1 as 800 Kelvin, T2 as 500 Kelvin, and T naught is 300 Kelvin, that is STP, that is at dead state. Pressure P1 is 900 kilopascal, P2 is 100 kilopascal, and P naught is 100 kilopascal again. Also, we have been given the value of CPR, and M dot is also given, that is given as 2 kg per second. Now, just to try to draw the exergy of a system, though exergy is not generally drawn, but still I will try to draw the pressure and temperature. At the pressure of 100 kilopascal, this is 100 kilopascal, and the temperature of 500 Kelvin, we will put here as 500. This is temperature in Kelvin, this is 500 Kelvin, and we have 800 Kelvin somewhere. We have 100 Kelvin as well somewhere here. Here we have a point from which it starts, that is exergy, that is being destroyed, and from 100 kilopascal pressure it goes to 900 kilopascal pressure, 900 and 800. Here we can find a point that comes here, at 800. This is where it goes. So, this is E1 and E2. This is where we have the inlet, and this is outlet, and here we have at 100 dead state. Here also with pressure dead state is 100 kilopascal. At 100 Kelvin also we have dead state. Now, the first part that is asked in the question is the specific flow exergy at inlet and outlet. I need to find E1 and E2. We know E is equal to H minus H naught minus T naught times S minus S naught. So, for ideal gas, that is given, we have H minus H naught is equal to Cp times T minus T naught. Also, to recall the relationship of entropy change for an ideal gas, that is S minus S naught this is S minus S naught, this is equal to Cp times log of T by T naught minus R times log of P by P naught. So at inlet, where temperature is 800 Kelvin and pressure is 900 kilopascal. So here we can put at the inlet E1 is equal to H minus H naught part and T naught into S minus S naught part. H minus H naught part is Cp into T minus T naught, this part. So this is Cp, Cp is equal to 1.005 into the inlet temperature minus outlet temperature, T minus T naught, 800 minus 300, this part, right? Now comes T naught into S minus S naught part, minus T naught is 300 and S minus S naught would be taken from this complete relation, that is Cp. Cp is 1.005 into natural log of the ratio of T by T naught, that is the inlet temperature 800 by at that state temperature 300 minus R times value of R is 0.287, that is given here. This into the natural log of the ratio of the pressures 900 kilopascal at that state temperature 100 kilopascal. This gives me the value of E1. To calculate it completely, we will find the value of E1 as 395.52 kilojoules per kg. Similarly, we can find at the outlet. At outlet, where T2 is equal to 500 and P2 is equal to 100. We have E2 as 1.005 into 500 minus the dead state 300 minus T naught times T naught is dead state 300 Kelvin times again this complete relationship here Cp 1.005 into the log of 800 by 300 was given for the inlet. For the outlet it would be 500 by 300, that is the outlet temperature by the dead state temperature, minus R, value of R is 0.287 times the natural log of the ratio of the pressures. The pressure at the outlet and at that state is 100 each. This gives me the value of E2 at outlet as 46.95 kilojoules per kg. So this is part 1 that is covered. Part 2 is exergy destruction rate. Exergy destruction rate. Exergy destruction rate, that is E destroyed, that we call it as capital E dot, that is exergy destroyed. This is equal to m dot into E1 minus E2. This is equal to m dot is our mass flow rate, that is 2 kg per second, into E1 minus E2. These values we have calculated here. 395.52 minus 46.95. We get the exergy restriction rate as 697.14 kilowatts. This was the one more problem in exergy. With this, I am closing my tutorial on the first 2 weeks of the course. I will come up with more tutorials in the coming sessions, and also I will try to talk about the virtual laboratory demonstration on thermodynamics. Then we'll close with thermodynamics. We'll move to the fluid mechanics. Thank you.